This is Module 12, Lesson 1. Congratulations, you've made it to the final module. We have a few more formulas to do this time, but it's also pretty short lessons. It's kind of like the last module. We have several lessons that don't have any practices to go with them. It's just concepts. You need to make sure that you understand them. And then we have a couple of formulas, so we will have some practice with those. So let's get started learning about waves. So what is a wave? It's a disturbance that travels through space. I gave you several different examples of them right here, like sound waves, radio signals, water waves, earthquakes. I'm sure that you could think of others. Now, if they travel through a medium or a material instead of space, they are called mechanical waves. Okay? There are three types of mechanical waves that we need to learn about. The first right here is called a transverse wave. Now, it's called a transverse wave because the wave and the medium will travel at right angles to each other. And if you think about it, that makes absolutely no sense whatsoever, right? So let's look at the image over here and see if we can make sense of it. So for example, pretend that this is a rope and you've got this person's hand here and they've taken it and they've flipped the rope up and down and they've made a wave travel through it. So hopefully you can imagine that what's happening is the wave starts at the person's hand and then it's traveling like this. It's traveling in general towards the wall over here. It's traveling to the right. So basically the wave itself is moving to the right. But what happens to the rope is the rope actually travels up and down and up and down. And notice in each of these instances we are making like little right angles. The direction of the movement of the wave and the direction of the movement of the medium are at right angles to each other. Hence the definition that's over here. The second type of wave is called a longitudinal or a compressional wave. I have two words. You do need to know both of those. Longitudinal and compressional I see all over the place. I'm not sure that one is used more often than the other. So there you have it. Longitudinal or compressional waves, they go parallel to the direction of the medium. So if you can pretend that this is a slinky and that the person has pulled the slinky back a little bit and then let it go, you know that the slinky is going to snap back to this direction. If you pull the spring back, it's going to snap back to its original position. It's going to return to its rest position. And what's going to happen is you're going to see a little bunch of part of the wave like moving back and forth right here inside of the slinky. I'll see if I can find a YouTube video of this because it's much better to see someone demo this. So look for a link to probably another Edpuzzle video in order to be able to see this. But you actually see this little piece move back and forth. While we're on this picture right here, because I don't have another one of it, the two parts of a longitudinal wave are called the rarefaction and compression. The compression is the little bunched up piece that you'll see moving back and forth down the wave. But the point is the compression will move left to right or right to left, and the slinky itself will move left to right. So everything is moving left-right. Everything is moving parallel to one another. The rarefaction are the spread out places, and I'll spell it down here in case you can't see it enough. It is called a rarefaction. I always have students who want to put an R in there and make it a rarefaction, and that is not it. It is a rarefaction, is the spread out part, and then the compression is the smushed together section. We're going to look at this one much more detailed here on the next slide. Thirdly, we have surface waves, which are actually just a combo deal of transverse and longitudinal, or transverse and compressional. You have those occurring at the same time. So let's look in detail now at a transverse wave, okay? The first word that's up here is medium. Media would be plural. It is the material that your wave is traveling through. That could be air, it could be water, it could be a rope, it could be a parachute that you're holding in gym class. If you ever did that in elementary school. Whatever it may be, it's the material that your wave is going through, the stuff it's traveling in, okay? In this particular case, if we pretend that this here is a rope, then that would be our medium there, okay? The crest. The crest is the highest point of a wave. So I wanted to switch to a highlighter and not a pen. I'll never find that color again. I have trouble seeing it. So the crest right here. Crest right here. This part of the wave, it's the highest point. It is the peak. Then you have the trough. The trough is your lowest point. Exactly like it sounds. You know, think animals drink out of a trough. A trough can't be shaped like a mountain. It's got to be shaped like a U so that water can go in it. Then you have the amplitude. Amplitude is always the distance from the rest position to either the highest point or from the rest to the lowest point. I did not label it up here as a word, but the rest position is if you have no movement in your wave and everything is just laying still. Like if this was our rope, you would just be holding it tight if it was fixed to a wall or something right here. If you just held it level with the ground, it would be at rest. No energy is moving through it. And then last but not least, we have wavelength. So wavelength is our, if I can get me another color here, we'll go with orange. Wavelength is the distance from, I put it this way, from a point on one wave to the same point on the next wave. Lots of times you'll see a definition of the distance from crest to crest, like this one. Right here's crest to crest, or the distance from trough to trough. But it doesn't have to be that. As long as you travel from the same point, so here's an example. This is about, I don't know, about a third of the way up the wave. As long as you're going from about a third of the way up to about a third of the way up on the next one, you know, the same exact point, then you also still have wavelength. It doesn't have to be from crest to crest to trough to trough. So see, both of these travel about a third of the way up. You still have one wavelength. Probably the three easiest places, if you have to calculate this, for you to find your wavelength would be here from crest to crest, here from rest to rest. Now you have to go one complete crest and one complete trough to get a whole wavelength. But that gives you a nice clean start and end point. And then to go obviously from trough to trough. Those three are the easiest just because you know that you're at the same point on each wave. There's no guessing to it. All right, our first calculation here. Our first calculation is with something called period. The period of a wave is the time that it takes for one wavelength. It would be measured in seconds. So, and it's always given in seconds. We don't do it in anything else. It has to do with the unit of frequency that's coming up next. It's simply the, just how long it takes for one wavelength to go past from crest to crest, trough to trough, or same point to same point. The frequency is a little f. Does it really matter? Yes, because we've used capital F forever. That stands for force. Lowercase f stands for frequency. So we do use a differentiation between our letters. Notice also we've used lowercase t in the past. That stood for time. Capital T stands for period. So our frequency has two possible units of measurement. That is either number, like number of waves per second, or hertz. So for example, you could say 3 per second. That means 3 waves per second. And that would be the same thing as 3 hertz. That means 3 waves per second, which is why the period has to be in seconds. Now, this formula right here is on your reference table. We are looking at page 4 of your reference table on the far right corner. It is our last little bit of formulas that we haven't learned yet. The time has come to do the rest of them. You are given this one. So you have that capital T, that period is equal to 1 over the frequency. They are reciprocals of each other. If you solve for F, you will come up with the F is 1 over T. So in other words, if you have a period of 3, you'll know that your frequency is a third. Or if you had a frequency of 4, then that means that your period would be a fourth. They're just the flip-flops of each other. So, you don't have to solve it this way. Just wanted to point it out. We're going to do some examples of this in just a second. Before we get to our examples of that, we have another formula. Now, my end goal is this formula down here, but I was going to walk us through how we came up with it. You don't have to derive it, but this is how we came up with it. This is an oldie. It's the very first formula that we actually learned how to do. It's the velocity equation. Ours actually has the V over the top of it. And does your wave velocity? No, your wave velocity is not. Our velocity equation was that you have basically displacement over change in time. You have change in position over change in time. So if we look at a wave, then what would be delta x would be one wavelength. And the symbol that we're going to use for wavelength is this. It's lambda. Looks like an upside down Y. The period would be our delta t. We learned that period is capital T. We also know that period is equal to 1 over f, 1 over the frequency. So if t is equal to 1 over frequency and our delta x is going to equal lambda, if we put those together and we just substitute, we'll have lambda on top in place of the x, and then we'll have 1 over f on the bottom for our time. Well, in order to, if you flip that, you get it out of the bottom, you'll have to multiply by the reciprocal. You will end up with, both of those times f. Those will cancel, and you end up with v equals lambda f. So this is our universal wave equation. It is the equation that we have to find the velocity, the wavelength, or the frequency of a wave. Our little v is yet again velocity. It's in meters per second, just like it was before. Lambda stands for wavelength. We are going to measure in meters. Since this is in meters, this must be in meters. And then we have little f, which is frequency. We just learned that that's in number per second or hertz, either way. If it's in number per second, then you can clearly see where if you had meters times some number per second, you end up with meters per second as your answer. So I kind of like that way. So let's do a couple of examples of this. You have a person playing a middle C on a piano, and it produces a sound with a frequency of this. So we know that this is F. What is the period of the sound wave? Well, if it's wanting period, it has to be this equation. It has to be the T is equal to 1 over F. And that would be 1 over 256, because right there's our frequency. Now, I do not want you to give me a fraction answer. I want you to give me a decimal. So very important, if I ask you questions like this on Canvas and you give me a fraction as your answer, you are not going to receive credit. I want a decimal number. That way you can also round it properly with sig figs. So if you do 1 divided by 256, nope, I punched that in wrong. Somehow I had an X in there. You get 0.00390625. Well, this has 3 sig figs, so this can have 3 sig figs. The 1 doesn't count. So remember, at numbers that are less than 1, you start counting from the first non-zero and go until you need to stop. So we're going to put 0.0039, and then that 0 would round up to a 1. So that, or you can do 3.91 times 10 to the negative third. And since it's, it's period, you have to have a unit. It's going to be seconds. Okay, so there's our answer for that one. That's not bad. What about an air horn that sounds at a frequency of this? So we have an F. If the speed of sound in air is 330 meters per second, so there's a speed, that's going to be our velocity. We're going to use those interchangeably here. What is the wavelength? So that is what we are hunting for. Well, clearly, this must be our other equation. We must be using V is equal to lambda F. Then we just plug things in. 330 is equal to lambda times 220. And I don't know what I get. I've already rounded it based on sig figs. I don't know if it comes out even or if I rounded it. Yeah, it comes out exactly. We get a lambda of 1.5, so says my calculator. It's perfect there. That has 2 sig figs. Let's check and see if that's okay. This has 2, and this has 2, so yeah, that's perfect. Now, what is our unit of wavelength? Meters, because this was in meters per second, so it has to be in meters. Hopefully y'all are like, this is super easy. Can't believe that it's this simple. Then we have another one more for us. It says that the distance between successive crests in a series of water waves is this. Well, I'm hoping that you recognize that as lambda. That is the wavelength. If it's the distance between crest to crest is what it means. And the crests travel this far in this many seconds. Whoa, like this one is a little bit more difficult. Calculate the frequency. What's the F? But the problem is this is another distance. This is telling me how far they travel in this much time. What we're going to have to do is we're going to have to figure out the speed of the wave. Now, I don't think I did problems like this, honestly, in your practice problems, but we can combine things together. These things went 8.6 meters in 5 seconds. Honestly, what I would do with this is not solve it. I'm just going to leave it like that and know that it's my velocity. So if that's my wave velocity, I've got velocity, frequency, and lambda. We can plug it into this other equation here. I am just going to copy these things over because that lessens the chances of me rounding twice. My lambda here is 4. And then we are hunting, I don't know why I'm putting it over something. Okay, there we go. And then we are multiplying that by some frequency. Well, now let's go and solve for f and see what we get. We're going to have 8.6 divided by 5, and then that will also then be divided by 4. So I get an f of 0.43. That's all my calculator says, okay? So let's check and see if we're okay sig fig wise. And since I did all this too, I'm not going to round, because a lot of you would have rounded and then it throws off this last answer. This had 2, 2, 2. I can have 2. So yes, that works perfectly. So 0.43, and then we need a unit. You can either answer 0.43 per second, or you can answer 0.43 hertz, as you hear my dogs barking. Okay, so now it's time for you to practice. You have a practice sheet. Go at it. If you have trouble, let me know. I'm available during office hours if you need my help.